Chapter 9, Stoichiometry. Stoichiometry seems to be one of the most difficult concepts we talk about throughout the year because it kind of combines everything that we have learned up to this point and puts it all together. Stoichiometry is talking about how much in a chemical reaction and comparing those amounts. We've talked about in chapter 6 why things come together. Talked about in chapter 7 how to bond them together. In chapter 8 we talked about the different chemical reactions and changes that take place. Now, we have not talked about how much of each substance to use. So in stoichiometry or in chemistry, stoichiometry is kind of like our recipe, our way to follow things. Before we start talking about stoichiometry itself, let's talk a little bit about proportional relationships. And the best example of a proportional relationship is a recipe. And what I've got here is a recipe for 5 dozen cookies. So let's kind of think of a stoichiometry type problem that you might see. All right. It says I have 5 eggs. How many cookies can I make? All right, so let's apply something that we learned in chapter 2 from dimensional analysis to think about how to solve this problem. Well, we always know in dimensional analysis that we start off with what we know. If we know we have 5 eggs, we also have to think about where we're going. We're going to how many cookies. So we need to find a way to relate eggs to cookies. And the best way to do that is to look at our recipe. Our recipe says that for every 2 eggs we have, we make 5 dozen cookies. So we can make that an equivalency factor and put that in our next set of boxes in our dimensional analysis set. So we put 2 eggs for every 5 dozen cookies. Eggs goes on bottom because it has to cancel. Dozens of cookies goes on top because that's what we're trying to get to. Again, eggs cancel. 5 times 5 is 25. Divided by 2 equals 12.5 dozen. That's just a simple stoichiometry type problem using a recipe, but it kind of shows kind of the process. And the most important thing in this conversion was our ratio of eggs to cookies. And just like in cooking, in stoichiometry, we also have a ratio that we're going to talk about. Stoichiometry is the mass relationship between substances in a chemical reaction. In the lab, we can't really deal with moles. We don't have a device that measures moles. However, we can measure the mass of things in grams and convert that using some of the math we learned in chapter 7 to convert stuff to the moles. Now, stoichiometry is based upon the mole ratio, and the mole ratio is indicated by the coefficients in a balanced chemical reaction. Now, I've got an example reaction right here. 2 magnesium atoms plus 1, there's an understood one here, oxygen molecule yields 2 molecules of magnesium oxide, or 2 formula units of magnesium oxide. Now, we can also talk about this in terms of just atoms or molecules. We can also talk about this in terms of moles. We can say that 2 moles of magnesium plus 1 mole of oxygen molecules yields 2 moles of magnesium oxide. So let's kind of think about this and look at the steps of actually solving a stoichiometry problem. The first step is to always get a balanced equation. If you need to learn how to balance equations, go back and look at the chapter 8 videos. Step 2 says identify the known and unknown problem. We will be working with several word problems in this chapter, so it would be helpful if you took either a highlighter or your pen and circled or squared either your known and unknown. Step 3 says to line up your conversion factors or set up your dimensional analysis boxes. Now, in stoichiometry, we only have 4 types of conversion factors that we use, 4 simple ones. And the first one is the mole ratio that we just talked about. The mole ratio allows us to go from moles of one substance to moles of another. That's the most important step in a stoichiometry problem. And we get the mole ratio from our balanced chemical equation. The second conversion factor is the molar mass. We learned about the molar mass in chapters 3 and 7. The molar mass allows us to go from moles of a substance to grams of that same substance, or vice versa, back and forth. Now, we get the molar mass from the periodic table, and that's dealing with solids. The molar mass helps us deal with solids. The third conversion factor is molarity. Molarity allows us to go between moles and liters of solution. Typically, molarity is given to us in our problem. When we're working with molarity, we're working with liters of solutions or liquids. So molar mass allows us to work with solids. Molarity allows us to work with liquids. The fourth and final conversion factor that we use in stoichiometry is the molar volume. And the molar volume allows us to go between moles of a substance to liters of that same substance in a gas. The molar volume allows us to deal with gases. Right now in this chapter we're going to learn what the molar volume is in an ideal situation. Next chapter, chapters 10 and 11, we're going to talk about what happens when that's not the same. But mole ratio allows us to compare moles to moles, which we must have in all of our problems. Molar mass allows us to deal with solids, allows us to go from grams of a solid to moles of a solid. Molarity allows us to go from liters of a liquid to moles of that liquid. And the molar volume allows us to go from liters of a gas to moles of that gas. So we can all plug it back into the mole ratio. Now the mole ratio is the key step in all stoichiometry problems. We must have a mole ratio in every problem. The fourth and final step in solving stoichiometry problems is to check the answer. Now, I talked a little bit about molar volume. Molar volume allows us to go from liters of a gas to moles. Well, there's a definition for that in this chapter. 1 mole of a gas is equal to 22.4 liters of that gas at STP. Well, we haven't talked about STP yet, but STP stands for standard temperature and pressure. Standard temperature and pressure is 0 degrees Celsius or 273.15 Kelvin and 1 atmosphere of pressure. In this chapter, we'll assume that all of our gas stoichiometry problems are talking about that gas at standard temperature and pressure. So let's look at this chart. We've seen this chart before where we've talked about going from moles to mass and moles to number of particles. In order to go from moles to mass in grams, we must use the molar mass. We get the molar mass from the periodic table. It's the red number on the periodic table. Remember, we only use 2 decimal places. We add it up for a different molecule or formula unit. Now, if we're going from moles to number of particles, then we always use Avogadro's number. If we're talking about individual atoms, individual molecules, individual formula units, we always use Avogadro's number, and it allows us to go between particles. Now, these are standard. We have done these calculations before. We've gone from mass to moles, then moles to number of particles, and etc., and back and forth, and started with moles and different things. What we're adding this chapter are 2 other conversions. The first is molarity. Molarity allows us to go from liters of solution to moles. Remember, this is dealing with liquids. We can go from molarity to moles. And the other conversion factor that we're using is the molar volume. The molar volume allows us to go from liters of a gas to the mole. Remember, in every stoichiometry problem, we always have to go back to the mole. The mole is the center part. We can make several calculations as long as we can get back to the mole. The mole is the key step.